In this video, I'm going to do a wrap-up of what we did last week in terms of introduction to forces and Newton's second law. So imagine that we have a car that is moving forward, but it is coming to a stop sign. So it's moving in this direction. And we want to understand how the forces are acting on this object so that we can explain and predict the motion. So the first thing that we're going to do is to start with a system schema. And so we know that we have the car, we have the road, and we have the earth. And the interaction between the car and the earth is the weight force. And the interaction between the car and the road, there are actually two of them. One of them is the normal force, and then I also have a force due to friction. So when we draw a boundary, we see that there are three interactions with the car, and that means that we need to have three forces on our free body diagram. So we draw a free body diagram. There's a lot going on right here. Don't bother scribbling it all down. Just do it a piece at a time. So we know that we have the weight force going down, so the weight force on the car by the earth. And we know that we have the normal force going up. So normal force on the car by the road. And then the third force is the force of friction. Because my velocity is forwards, in order for the car to slow down to get to the stop sign, the force has to be in the opposite direction, slowing it down from the velocity. So we have a force in this direction, the friction force on the car by the road. We can, if I say that the weight force on the car is 20,000 newtons, and I just tell you that, I know that the normal force is also going to be 20,000 newtons because they're equal, because the motion in the vertical direction is constant. Okay, motion in the vertical direction is constant. In other words, it's not moving vertically, not moving up or down. So whatever the weight force is equal to, the normal force is equal to. This will not always be true, but it's true in this case. So when I look at the net force, I add up all the forces. So the net force is the sum of all the forces on the car, and I know that it is the normal force plus the weight force plus the force due to friction. Three forces, I just add them all up. Now, when I think about it, I know that the weight force is 20,000 newtons, and that's acting down, so I subtract. The normal force is equal, that's also 20,000 newtons, so the only force left over is the force of friction. And so I end up with this net effect that the net force is only the force due to friction on the car by the rope. And what we learned with the Newton 2 exploration is that this net force is equal to the mass times the acceleration. Okay, net force is equal to the mass times the acceleration. Now, suppose I just told you that the net force is 50 newtons. That means if I know the mass of the car, I can figure out the acceleration, or how much the car is slowing down, and I can figure out, is it going to stop in time before it gets to the stop sign or something like that. So how do I figure out the mass of the car? Well, I know that the weight force is equal to m times g. I learned that in the textbook on page 135, and we make this approximation on the Earth that g is 10 newtons per kilogram. And so when I solve this, I find out, so I divide both sides by 10, and so I've got 2,000, it's actually going to end up being kilograms, is equal to the mass of the car. So that's an important thing to know. So what is the mass of the car? Oh, all right, mass of the car, we figured out was 2,000 kilograms. And so now I can go back to this idea of F is equal to ma, and so A is equal to force divided by mass. So my net force is 50 newtons. I just figured out the mass was 2,000 kilograms, and so that gives me 0.025 meters per second squared. And I'm putting in negative because I know it goes to the left, and this is the correct unit for acceleration. Okay, so a lot happened, a lot of information. Hopefully you stopped and took notes. So what we should be able to do now, based upon this, is to determine the numerical value of forces in a free body diagram based on the motion, determine the net force from the free body diagram, determine forces from the net force, and determine the mass from the weight force. People keep asking me about this. I just don't know what else to say. Fw equals mg. And then also determine the acceleration from the net force. So you might look at that list and think, oh my gosh, I can't do any of that stuff, but I want to show you that you can. So this is a problem from positive physics. We will work through it. So we've got a 55 kilogram bicyclist. She's generating a 210 Newton force, and she has a 60 Newton drag. So we can start filling in our diagram. She's 55 kilograms, and so this weight force is going to be m times g, and since g is 10, that means this is going to be 550 newtons. And she's not moving up or down, so that means that the normal force is 550 newtons. Her forward force is going to be 210, and her backwards force is going to be 60, because that was the drag. And so the net force, therefore, is going to be 150 newtons. Sorry, 150, newtons. And the way I got that was, I know that F net is going to be equal to normal plus thrust plus drag plus weight. And so this is going to be 550 plus 210. Drag is subtracted and weight is subtracted. And when I do that math, I get 150. Her mass is 55. That was given in the problem. And her acceleration, therefore, is going to be F net divided by m. And so that's going to be 150 divided by 55. I did not calculate this yet, so I'm going to do that right now. And so that's 2.7 meters per second squared. And her speed, it's a drop down, it's increasing. So believe it or not, we just did most of those things or a derivative of those things in here. Are all the forces on the bicycle balanced? No, because there's a net force of 150.